Sit in a quiet room. No one is with you. And somewhere out there, a person you love, a star you have never seen, a speck of dust drifting in the dark is, according to physics, genuinely linked to you. Why can you never use it to reach across the empty space? To answer that, we need three things. What the link actually is, the one word that fooled almost everyone, and the mathematics that proves it can never touch you. Let me start where the confusion starts, because the whole trouble lives in a single ordinary word. The word is connected. When you hear that two particles are connected across any distance, your mind does something automatic and reasonable. It pictures a thread, a taut, invisible line running through the dark, and along that line, something travels. A pull, a message, a whisper of presence. That picture is why the idea feels so warm, and it is why the phrase "spooky action at a distance" has escaped the physics lab and ended up on posters and in meditation apps. And here is the thing I want to be honest about from the first minute. The picture is not stupid. It is half right. There really is a link. It has been measured, confirmed, hammered on by the most careful experiments physics can build, and it will not go away. The half that is wrong is the thread. There is no thread. Nothing travels. Nothing can be felt. And the astonishing part, the part I keep returning to, is that the very same mathematics that makes the link real is what proves it can never reach you. The subject at the center of all this is quantum entanglement, a correlation between two systems so deep that you cannot describe either one on its own without describing the pair together. That is the whole definition, and it matters that we get it right at the start, so hold on to it. Entanglement is not a substance passing between two things. It is a shared description that refuses to come apart into two separate stories. Let me make that concrete, because abstract definitions slide right off the mind. Picture two accountants each handed a sealed ledger, one flown to Tokyo, one kept in New York. Open either ledger alone, and every entry looks like meaningless random noise. No pattern, no signal, nothing you could act on. It is only when the two accountants later sit at the same table and lay their ledgers side by side that a pattern leaps out. Every entry in one matches, in a precise coded way, an entry in the other. That matching is the correlation. But notice what the accountant in Tokyo experiences while sitting alone. Nothing. No change, no flicker. His ledger reads exactly the same whether or not the New York ledger has been opened, read, burned, or buried. This is not a loose metaphor I am reaching for. It is, as we will see, exactly what the mathematics says, down to the last symbol. The local story never changes. And that fact, that stubborn, unmovable local sameness, is the whole answer to the question in the title. But we have to earn it. So how do we know the link is real at all, and not clever bookkeeping, sealed envelopes with the answers written inside from the start? That question has an answer, and it is one of the cleanest results in all of physics. In 1964, a physicist working quietly at CERN in his spare time turned a philosophical argument into a number you could measure. His name was John Bell, and what he proved is that if the particles carried hidden, pre-written answers, the sealed envelope picture Einstein preferred, then their correlations could never exceed a certain ceiling. Quantum mechanics predicted the ceiling would be broken. For decades, the experiments crept closer, and then, in 2015, 3 separate laboratories closed every remaining loophole at once. But keep the verdict in mind, because everything we build stands on it. The correlation is real. It is not hidden envelopes. Local, pre-written answers are dead. How real? Let me give you one number that ends the argument. In 2015, a team in Vienna, led by Giustina, measured the strength of the correlation and found that the probability it could be explained by any local pre-existing arrangement was below 3 × 10⁻31. That is an 11.5 standard deviation result. To feel what that means, physicists announce a discovery at 5 standard deviations. This was more than double that, in the tail of a bell curve so far out that if you ran the experiment every second since the universe began, you would not expect the fluke even once. The link is not a maybe, it is one of the most confirmed facts we have. So we are left holding two things that seem impossible together. The correlation is real, confirmed past any reasonable doubt, and the person alone in the quiet room feels nothing, can send nothing, can use it for nothing. How can both be true? That contradiction is the engine of everything that follows. So let me name the 4 walls that stand between the real connection and any possible feeling of it. The answer is not one idea, but 4, and each is airtight in a different way. There is a wall against information, a wall against perception, a wall against coherence, against the link surviving at all in anything as large as a body, and a wall against sharing, against the link spreading to everything the way the wellness slogans promise. We will walk each wall in turn, touch the mathematics of each, and only at the very end weigh what all 4 together leave standing. Start with the first wall, the one that does the heaviest lifting, because it is not an experimental limit that a better machine might someday overcome. It is a theorem. It is called the no communication theorem, and what it says, in plain words, is this: nothing you do to your half of an entangled pair can produce any change at all, in what a distant partner can observe about their half. Not a slow change, not a weak change, no change. And I want to build this carefully, because when you see why it is true, the eerie feeling of entanglement does not vanish, but it settles into something you can hold. To get there, we need one piece of mathematics, and I promise to state what it means before I state what it looks like. The idea is this: when 2 systems are entangled, the full, honest description lives in the pair, in the joint state. But suppose you only have access to your half. You are the accountant in Tokyo. You want to know the complete list of everything you could possibly measure right here on your ledger alone. Quantum mechanics has an exact object that answers that, and only that. It is called the reduced density matrix. You get it by taking the full description of the pair and mathematically averaging away, tracing out everything about the distant partner you cannot touch. The operation is called the partial trace, and the equation is written ρ minus a equals the partial trace over b of ρ minus a minus b. Ρ minus a minus b is the full joint description of both halves. Ρ minus a is what is left after you erase the distant half, the complete summary of everything the Tokyo accountant can ever see. Let me turn that symbol into something physical before we go anywhere. Think of a photograph of 2 dancers taken with a long exposure while one of them stays perfectly still. To describe the still dancer alone, you would smear away, average over, every position the moving dancer passed through. What is left is a clean, fixed image of the one who did not move. The partial trace is exactly that smearing away of the far partner, and ρ a is the clean, fixed image that remains. Now here is the whole point, the hinge the entire theorem turns on. You can prove, in a few lines of algebra, that whatever the distant partner does to their half, measure it, rotate it, smash it, anything physics allows, the smeared away image, ρ a, does not change. It is mathematically invariant. As the standard proof puts it, the fact that this quantity never changes as the far partner acts is the conclusion of the whole theorem. Sit with what that means, because it is the answer to the very first question the title forces. If they are really connected, why can I never feel it, never send even a single bit? Because the complete list of everything you can observe on your side is fixed, and nothing anyone does anywhere can move it. There is no local needle that twitches when the distant partner acts. Not a subtle one. Not one a sensitive enough instrument could someday catch. The needle cannot exist because the object it would have to read is provably frozen. This was not obvious, and it was not proven in one stroke. Philippe Eberhard laid the groundwork in 1978. Then Giancarlo Girardi with Alberto Rimini and Tullio Weber proved in 1980 that the measurement process itself could carry no faster-than-light message, and later extended the proof to cover every subtle kind of measurement quantum mechanics allows. Eberhard and Ross closed it inside the full framework of quantum field theory in 1989. 4 decades of the sharpest people in the field trying and failing to find a crack, because there is no crack.
I know how this feels from the inside, because the word connection fights you the whole way. If nothing changes on my end, how can there be a connection at all? Here is the resolution, and it is subtle enough that it is worth slowing down for. The connection is not in either half, it is in the relationship between the two lists, a relationship that exists, but that neither party can see alone. Go back to the 2 accountants. Each ledger, read alone, is pure noise, and stays pure noise no matter what happens to the other. The pattern is real, but it lives only in the comparison, and to compare, the accountants have to physically travel, or phone, or mail their ledgers to the same place. That comparison moves at the speed of an ordinary message, no faster. The correlation is real, and it is mute, and both at once, and the mathematics is why. What does it mean that a connection can be perfectly real and carry nothing? I return to that question often, and not because it is comfortable. Because it forces a distinction the everyday word connected does not have. In ordinary life, connected means something passes. A wire carries current, a phone carries a voice, a rope carries a pull. Quantum entanglement is a connection with none of that. It is a shared fact about 2 things that shows up only when the 2 things are brought back together and checked. And that first wall, the no communication theorem, standing on the invariance of the reduced density matrix, is not a wall a better experiment tears down. It is a wall built out of the same mathematics that makes the connection real in the first place. That leads directly to the second wall, and it is the one people find hardest to accept, because it feels like it should have an exception. Fine, no signal. But surely, if I were entangled with someone I loved, I would feel something. A pull, a presence, some faint registering in the body of the distant event. This is the perception wall, and the honest answer is that it is the same wall as the first one, seen from the inside of a living body. Perception is measurement. Every sense you have works by some physical quantity in your body changing in response to the world. Light bending a molecule in your eye, pressure bending a hair in your ear. For you to feel a distant, entangled partner's action, some locally observable quantity in your body would have to change when they act. But we just proved that quantity is frozen. Rho A does not move. So there is nothing for a nerve to fire on, nothing for a receptor to catch. Not because the connection is too weak to feel, because there is, provably, no local change to feel. The body is exactly the Tokyo accountant, and the far ledger's outcome leaves its own ledger untouched. Before I go on, hold that against something you can touch right now. Wrap your hand around a warm cup. What you feel is heat, molecules in the cup jostling molecules in your skin, a physical quantity changing on your side of the boundary. That is what perception is, a local change. Entanglement offers no such change ever. The cup can warm you across an inch of ceramic. A distant entangled partner cannot warm you across the room because there is nothing on your side that moves. Hold on to that difference because it is the whole reason the feeling of connection and the physics of connection are 2 different animals wearing the same word. If you are following this and finding that it changes something in how the quiet room feels, a quiet tap on the subscribe button helps these longer walks reach more people who like to think this slowly. Now the third wall, and this one is different in character, because here we leave the clean world of 2 ideal particles and walk into the world you actually live in, made of bodies and dust and warm air. And in that world, a new and even more merciless effect takes over. It is called decoherence, and to understand it, you have to give up the picture of two lonely particles holding hands across empty space. Nothing in your world is lonely. Everything is drowning in an ocean of other particles. Air molecules, photons of light, the faint hiss of heat radiation, even the ancient afterglow of the cosmos itself. Here is the idea, and it inverts everything the intuition expects. Decoherence is what happens when a quantum system stops being isolated and starts getting entangled, not with one clean partner, but with the countless particles of its environment, all at once, uncontrollably. And the more thoroughly a thing entangles with its surroundings, the more completely its own delicate quantum behavior, the interference, the superposition, the connection you could in principle use, gets smeared out and buried across all those particles until, locally, it looks exactly like ordinary classical stuff. The connection does not break, it disperses. It is spread so thin across so many particles that no one, anywhere, could ever gather it back up. Who worked this out, and how fast does it happen? The foundations were laid by a German physicist, H. Dieter Zeh, who argued in 1970 what almost no one wanted to hear: that a large object is never, even in principle, isolated from its environment, so the textbook picture of a clean quantum system was a fiction for anything bigger than a few atoms. Then, in 1985, Joos and Zeh did the thing that turns an idea into a science. They calculated the rate. They wrote down how fast the environment destroys a superposition, and the key quantity is called the localization rate, written with the Greek letter lambda. The relation they found is written: g equals 1 minus lambda times the square of the position difference. Let me translate before the symbols harden. Imagine a small object smeared out into being in two places at once, a tiny distance apart. The quantity g measures how much quantum connection between those two locations survives after the environment has taken a swing at it. Lambda is how hard the environment hits. And that separation is squared, meaning the bigger the object, the wider its two ghostly positions, the more violently the effect scales up. Now picture what lambda actually is, physically. Think of trying to keep a secret whispered between two people in a silent library versus in a stadium during a goal. In the library, the secret survives. In the stadium, every passing roar carries a copy of it away until it is hopelessly public. Lambda is the roar rate, and here is the number that stopped me the first time I saw it. For a single grain of dust, 10 micrometers across, 4 10,000ths of an inch, the kind of mote you see drifting in a shaft of sunlight, sitting in ordinary air, the localization rate from air molecules alone is about 10 to the 36th per square centimeter per second. 10 to the 36th, that is a 1 followed by 36 zeros. It means a dust grain's quantum superposition, if you somehow made one, would be erased so fast that no instrument could ever catch it in the act. The connection to the world is not weak. It is so overwhelming, so instantaneous, that the grain is yanked into ordinary classical behavior the moment it exists. Take a breath, because I know this is a lot of machinery. Here is why it matters to the mote in your own window. That drifting speck you have watched 100 times, lit gold in the afternoon light, is not sitting quietly apart from the world. It is being measured, ceaselessly, 10 to the 36th times over, by the air around it. It is one of the most thoroughly connected objects you will ever see. And that total connection is exactly why it behaves like a perfectly ordinary, separate, classical speck. Let that reframe what connection even means for a moment, and then let us push further. Because it gets stranger, and this is one of the details I have never heard explained plainly outside the technical papers. You might think, fine, air is violent, put the grain in a vacuum. Take away the air, the light, the heat, surely then it stays quantum. And here is where the universe closes the door completely.
Joos and Zurek worked out that even if you removed everything, every air molecule, every particle of warmth, every ray of sunlight, the cosmic microwave background alone, the faint cold afterglow left over from the universe's earliest era, at just under 3 degrees above absolute zero, is enough on its own to destroy that dust grain's superposition on a timescale of about 1 second. You cannot hide from it. There is no box you can build, no vacuum you can pump, no shield you can raise, because the afterglow of the cosmos itself soaks through everything. What does it mean that the oldest light in existence is still busy, right now, prying apart the last quantum secrets of every dust grain in the dark? It means isolation, for anything larger than a molecule is not merely hard, it is impossible. And now the second wall and the third wall reach out and touch each other, which is the connection I find most beautiful in all of this. The reason you cannot feel a distant entangled partner, and the reason a dust grain cannot stay quantum, are the same reason. Both are about a system getting so entangled with its surroundings that its quantum connection stops being locally accessible. In the two-particle theorem, we averaged away the far partner and found the local view frozen. In decoherence, the environment does that averaging for you, automatically, 10 to the 36th times a second, whether you like it or not. The mathematics of the partial trace and the mathematics of decoherence are the same mathematics. That is not a coincidence. It is the deep structure of why the quantum world hides itself the moment things get large. Which brings the whole question home to the one place it cannot hide from, your own head. If the connection cannot be felt because there is no local change, and cannot survive in large objects because of decoherence, then what about the brain? Because if there is any physical seat for a felt cosmic connection, surely it is there. This is where a physicist named Max Tegmark did something bracingly honest in the year 2000. People had speculated for years that consciousness might run on quantum effects, that the mind might be a place where superposition and entanglement do real work, which would leave a door open for exactly the kind of connection the title asks about. So Tegmark calculated the numbers. He asked how long a quantum superposition could survive inside the warm, wet, electrically noisy tissue of a living brain before decoherence destroys it.
His answer is one of the starkest comparisons in the field, so let me set it out plainly. The decoherence time inside the brain, how long any quantum connection lasts before the environment shreds it, comes out between 10 to the minus 13th and 10 to the minus 20th of a second. The timescale on which the brain actually does its work, on which a neuron fires or a thought forms, is between 10 to the minus 3rd and 10 to the minus 1st of a second. Line those up. The quantum connection dies at least 10 trillion times faster than a single thought can form, and by the upper estimate, 10 to the 19th times faster. That is not a close race. Tegmark's conclusion was direct. The brain is a classical machine. Whatever a thought is, whatever the feeling of connection to a distant person is, it is not built on surviving quantum entanglement, because no such entanglement survives long enough inside your skull to matter. Now, science is not a place where one calculation ends a conversation, and I want to be fair to the disagreement because it is real. Within 2 years, Stuart Hameroff, Roger Penrose's collaborator, together with colleagues, pushed back, arguing that special conditions inside neurons, ordered water and shielding effects, might stretch quantum coherence far longer than Tegmark allowed, perhaps by 1,000-fold. And even 1,000-fold, notice, still leaves the connection dying billions of times faster than a thought. The disagreement is about how badly the brain loses the race, not whether it loses it. What does it mean that even the most generous defenders of quantum mind cannot get coherence to survive as long as a single heartbeat? It means the felt connection you are sitting with in that quiet room, whatever it is not a quantum thread reaching out of your neurons. But I promised fairness, and there is a genuine frontier here, so let me be precise about where quantum effects do reach into biology.
because the honest picture is more interesting than a flat no. There is one case, the best supported case we have, where quantum coherence appears to do real biological work, and it is not in the brain, and it is not entanglement you could feel. It is in the eye of a migratory bird. A physicist named Klaus Schulten proposed in the 1970s that birds might navigate by sensing the Earth's magnetic field through a quantum effect. And decades later, the pieces came together around a molecule called cryptochrome. When light hits it, it makes a pair of molecules, each carrying an unpaired electron spin, a radical pair, and the delicate quantum relationship between those two spins is sensitive to the direction of the magnetic field. In 2021, a team studying the cryptochrome from the European robin showed in the laboratory that the molecule does have exactly this magnetic sensitivity. This is real. This is functional quantum biology.
But look closely at what it is and what it is not, because this is the pattern-breaking detail. The whole effect works on a timescale of about a millionth of a second, and over the span of a single molecule, a few billionths of a meter. It is quantum spin coherence doing a job inside one tiny structure, and it works precisely because it is fast and local, protected from the environment for just long enough. It is not a long-range connection. It carries no signal from a distance. A bird does not feel a magnetic partner across a continent. It runs a chemical compass inside its own eye for a microsecond at a time. So even the one clear success of quantum biology confirms the walls rather than breaching them. Quantum effects survive in living things only when they are fleetingly brief and fantastically small. Stretch them to the size of a body, the length of a thought, the distance between two people, and decoherence has already won. There is one more record worth holding, because it marks exactly where the border sits. How large a thing can we push into a quantum superposition before the world tears it apart? In 2019, a team in Vienna and Basel, led by researchers including Yakov Fine, sent molecules through a 2-meter interferometer. Molecules built of 2,000 atoms, more than 25,000 times the mass of a hydrogen atom, and held them in two places at once for more than 7 milliseconds. The largest was a single monstrous molecule, more than 40,000 protons, neutrons, and electrons together, with a quantum wavelength 1,000 times smaller than a single hydrogen atom. It is the largest object we have ever caught behaving quantum mechanically, and it is still unimaginably smaller than a grain of dust, let alone a fingertip. That is the frontier. 2,000 atoms, 7 milliseconds, in a machine built specifically to hide it from the world. Everything larger, everything warmer, everything in the open air has already crossed into the classical. I keep coming back to a single reframing, and it is the one that genuinely rearranged how I think about this whole subject. We say a body is not connected to distant things because it is isolated. That is exactly backward. A body is not connected in any usable way precisely because it is not isolated, because it is so completely, so violently entangled with everything immediately around it that whatever connection it might have had to anything far away is diluted into invisibility. You are drowning in connection. That is why you cannot feel any single thread of it. A connection so total it is operationally indistinguishable from none at all. That paradox is the doorway to the fourth wall, and it is the one that quietly demolishes the most beautiful version of the belief, the wellness idea that everything is entangled with everything, one great web, and that this web is what we might feel as not being alone. It turns out the mathematics of entanglement forbids exactly that. The principle is called the monogamy of entanglement, proven in the year 2000 by 3 physicists, Valery Kaufman, Joydip Kundu, and William Wouters. And the name is not a metaphor. It means what it says. If a system is maximally entangled with one partner, it cannot be entangled with anyone else at all. Let me make that vivid before the equation, because it genuinely runs against everything the slogans promise. Think of a person with a fixed, finite budget of trust, and suppose trust worked the way entanglement does. If they give the whole of it to one person, total, complete, maximal, then there is mathematically none left for anyone else. Not a little, none. And the more they spread it thinly across many people, the weaker each individual bond must become. You cannot be maximally deeply entangled with everything. The budget forbids it. The mathematics that captures this uses a measure of entanglement called the tangle, and the relation is written: tangle A minus B plus tangle A minus C is, at most, the tangle of A with B and C together. In plain words, the amount of entanglement a system A can share with a partner B, added to the amount it can share with a third party C, cannot exceed the total entanglement A has available to give. There is a fixed budget, and it must be divided. Turn the symbols into a picture. Imagine a single candle whose flame you want to use to light others. Light one candle fully, and you have spent the flame. The more candles you try to touch it to at once, the weaker and more flickering each new flame becomes. Entanglement is that flame. It cannot blaze at full strength in every direction at once. Now feel what monogamy does to the slogan. The popular idea says the deeper the connection, the more it links you to everything. Monogamy says the exact opposite. In the quantum sense, the deeper two systems are connected, the more completely they are cut off from everything else. Maximal connection is not maximal togetherness, it is maximal exclusion. The two accountants whose ledgers match perfectly are, by that very perfection, sealed off from every other ledger on Earth. What does it mean that the strongest possible connection is also the most isolating one? It means the dream of a universal web where all things are deeply entangled with all things is not merely unproven, it is mathematically prohibited. The connection is real, but it is jealous, exclusive, and finite. The opposite of the boundless web the word connection invites us to imagine. So there are the four walls, laid out fully, each standing on its own mathematics. Information, the no communication theorem, no message can pass. Perception, reduced state invariance, no local change can be felt. Coherence, decoherence, no macroscopic connection survives long enough to matter. Distribution, monogamy, strong connection cannot be shared with everything. And I have been careful all this way to present these as what they are, and not yet to weigh them against each other or against the deepest thing they leave open. That is the honest work still ahead. But first I want to go deeper into the one idea that pushes hardest against everything I have said, because there is a version of quantum mechanics in which you and the distant world genuinely are one single entangled state, and it deserves its full hearing. That idea came from a graduate student at Princeton in the 1950s. His name was Hugh Everett III, and he was troubled by something at the heart of the standard textbook account. The idea that a quantum system evolves smoothly and predictably right up until someone measures it, at which point it mysteriously and instantly jumps or collapses into a single definite outcome. Everett found that account, in his own blunt words, hopelessly incomplete. He called it a philosophic monstrosity for granting reality to the everyday world while denying it to the microscopic one. So he asked a radical question. What if there is no collapse at all? What if the smooth, deterministic evolution, the one described by the master equation of quantum mechanics, never stops, never breaks, and applies to absolutely everything, including the measuring instrument, including the physicist, including the entire universe? The result is what Everett called the universal wave function, and it is the most complete expression of the idea that everything is one entangled state. Written as an equation, it is the familiar Schrödinger equation. IH bar times the rate of change of the state equals the energy operator acting on the state, but now applied not to a single particle, but to the cosmos entire. Let me translate that before it hardens into symbols. It says the total description of everything evolves like a single, unbroken wave,
rolling forward smoothly forever, with no jumps, no collapses, no special moments where reality picks an outcome. One state, one universe-sized wave. Everything inside it, you, me, the distant star, the drifting dust, a piece of that one state. If that is true, then the deepest reading of the title is literally correct. You are not merely connected to the distant world, you are, with it, a single, indivisible, entangled whole. So why does it not feel that way? Everett's own answer is contained in a phrase he insisted on, the relativity of states. He wrote that it is meaningless to ask for the absolute state of a subsystem. One can only ask for its state relative to a given state of the rest. In other words, there is no view from nowhere in which you see the whole wave. There is only your view, from inside, relative to your own branch. And what carves those branches? What makes your slice of the universal wave look like an ordinary classical world with definite objects in definite places is decoherence, the very same effect. The universal wave function says everything is one connected state, and decoherence is precisely the reason you will never experience it as connection. The two ideas are not rivals, they are two halves of one answer. I had to sit with that for a long while when I first understood it, because it is genuinely vertiginous. The strongest possible statement of cosmic connection, the entire universe as a single entangled state, comes bundled with the exact mechanism that guarantees you can never feel it. It is not that connection is absent, it is that connection, this total, is, from the inside, indistinguishable from separation. The whole is one. Every part experiences itself as alone, both at once, and the mathematics is why.
How did the idea of a single connected quantum state come to be taken seriously rather than dismissed as philosophy? Through the slow, unglamorous work of making decoherence quantitative, the work of Zurek and Joos we have already walked through, and then a further step taken by a physicist named Wojciech Zurek. Zurek asked a sharp question. If everything is a smooth quantum wave with no collapse, why does the world we see have such definite, stable properties? Why do objects have positions that stay put, rather than smearing into quantum blurs? His answer is a mechanism he named einselection, environment-induced superselection. The environment, constantly measuring everything, does not pick randomly. It picks out a special set of stable states, he called them pointer states, that survive its relentless monitoring. Position is one. That is why the dust grain has a location and not a blur. The environment has selected location as the property it robustly records. And Zurek went one step further, into an idea he called quantum Darwinism, and this is where the abstract becomes testable. The environment does not just destroy the fragile quantum connection, it makes redundant copies of the surviving classical information and scatters them everywhere. The dust grain's position is stamped over and over onto the countless photons that bounce off it, so that many independent observers can each read the same value without disturbing it. That redundancy is why we all agree on where the grain is. Objectivity itself emerges from the environment broadcasting the same classical fact a million times over. And this has been tested. In 2019, a team using nitrogen vacancy centers, atomic defects inside diamond, showed experimentally that a controlled environment does exactly this, eliciting stable pointer states just as the theory predicts. Other groups confirmed it in photonic systems, and later in superconducting circuits. The emergence of the ordinary, definite, classical world out of the quantum one is not a handwave anymore. It is measured. Notice what this does to our question. Quantum Darwinism explains, in tested detail, why the world looks classical and separable even if it is fundamentally one connected quantum state. The connection is not broken. It is buried under a mountain of redundant classical copies, and what you perceive is only the copies. You never touch the underlying entanglement, because everything your senses can reach is the environment's broadcast,
not the fragile quantum original. What does it mean that objectivity, the shared solid world we all agree on, is built out of the destruction of quantum connection? It means the very stability of the reality around you is the residue of connection being erased and overwritten, endlessly, everywhere, faster than thought. Let me pause here and ground all this abstraction in something you can hold in your hand, because we have climbed a long way. Take your house key. It has a definite shape, a definite position in your pocket, and it stays that way whether or not anyone looks at it. That is Ein selection at work, the environment ceaselessly selecting and recording its position. When you hand it to someone and they see the same key in the same place you did, that shared agreement is quantum Darwinism. The key's classical facts copied across countless photons, readable by anyone, disturbing nothing. Everything solid and dependable about that key is the visible face of quantum connection being dispersed and overwritten. Hold that, because it turns the whole intuition inside out. The solidity of your world is not the absence of quantum connection. It is what quantum connection looks like after the environment has finished with it.
Now we can go somewhere most treatments never reach, because there is a place where all these threads, entanglement, entropy, the survival and destruction of information, knot together into one of the deepest open problems in physics. And it turns out to be about the most extreme objects in the universe. In 1993, a physicist named Don Page asked what happens to entanglement when a black hole slowly evaporates. A black hole radiates away, particle by particle, over unimaginable spans of time. Page tracked the entanglement between the radiation that has escaped and the black hole that remains, and he found that it does not grow forever. It rises, reaches a peak at a moment now called the Page time, when the radiation carries as much entropy as the black hole itself, and then falls back down. That curve, the Page curve, is the fingerprint of information being preserved rather than destroyed. It says the connection between the inside and the outside of a black hole is real, is enormous, and is governed by the same monogamy that governs two particles in a laboratory, because a piece of radiation maximally entangled with the early radiation cannot also be entangled with the black hole's interior. And that exclusivity is exactly what forces the curve to turn over. The very same principle that forbids a universal web of connection is what may rescue information from a black hole. I find that connection between the smallest theorem and the largest object genuinely staggering, and it is a thread physics is still actively pulling. And I have kept a promise made near the start. I have not yet weighed these ideas against one another, or asked which of them is right, or named honestly the single question that all of them leave open. Now that we have seen why the connection is real, why it carries no signal, why it cannot be felt, why it cannot survive in a body, and why it cannot be shared with everything, one last uncomfortable question remains, and it is not the one you would expect. It is not whether the connection can reach you, we have settled that. It is what the connection actually is. And that question, it turns out, is the one place where the mathematics genuinely runs out. Let me draw the threads together, because everything we have built now has to be weighed. Start with what is settled, and be precise about why it is settled. The no communication theorem and the invariance of the reduced density matrix are not interpretations. They are theorems, mathematical consequences that hold no matter which story about quantum mechanics turns out to be true. Whether the universe is one Everettian wave, or guided by hidden trajectories, or something else entirely, the reduced state stays frozen and no signal passes. That is why I can say, with the full confidence of the mathematics, that the connection carries no message and can never be felt. It is not a hopeful reading of the evidence. It is a locked theorem, and every serious interpretation of quantum mechanics obeys it. Add decoherence and monogamy, and the case closes on the macroscopic question completely. The leading scientific account of why our world looks classical, the Everett and decoherence picture, sharpened by Zurek's Ein selection and confirmed by the quantum Darwinism experiments in diamond and photons and superconducting circuits,
explains, quantitatively and with tested predictions, why no felt connection can exist in anything as large and warm as a body. Does that picture fit the evidence? On the question we actually asked, can the connection reach you, it fits perfectly, and nothing competes with it. The decoherence rates are measured, the pointer states are observed, the brain's timescales are calculated, and the frontier of macroscopic superposition sits at 2,000 atoms in a vacuum, a universe away from a fingertip. Every wall holds. Now, does that mean the Everettian universal wave function is proven true? No, and this is where I have to be scrupulously fair, because the science and the interpretation are different questions. Everett's picture is the strongest of the no-collapse accounts, and decoherence gives it real explanatory muscle. But it carries a genuine unpaid debt. Deriving the ordinary probabilities we observe, why we see one outcome with a particular frequency, from a theory in which every outcome happens somewhere, remains contested. That is a real weakness, honestly, on the books. So the evidence supports the decoherence mechanism strongly, while leaving the full interpretation open. And there are serious alternatives, each of which I want to weigh on its own terms rather than wave away. One family says the whole puzzle dissolves because we were wrong to imagine a single observer-independent state at all. This is relational quantum mechanics, developed by Carlo Rovelli, and alongside it a view called QBism. Rovelli's proposal is that physical properties are never absolute. They exist only relative to another system doing the interacting. On this reading, the spooky distant collapse was never a physical event. It was one observer updating information defined relative to them. There is no thread to feel because there is no absolute global state to be threaded. Rovelli is careful to say this is not a claim that reality needs a human to exist. As he puts it, he has no reason to think reality comes into being only when it interacts with him, and not when anything interacts with anything else. QBism takes a nearby but distinct route, treating the quantum state as an agent's own calibrated expectations rather than a picture of the world. Where do these fit the evidence? They fit it completely. They are built to reproduce every quantum prediction, and they resolve the spookiness elegantly. Where do they strain? They are charged fairly with buying that resolution by stepping back from a fully observer-independent physical reality, which many physicists are unwilling to give up. That is a real cost, and the evidence does not force anyone to pay it. Then there are the accounts that try to save the older intuitions by paying a sharper price. Superdeterminism, defended by Gerard 't Hooft and by Sabine Hossenfelder and Tim Palmer, restores locality and determinism by dropping the assumption that experimenters choose their measurement settings independently of the system. If that assumption fails, Bell's theorem loses its grip and the world can be local after all. The difficulty is one its own defenders admit plainly. Hossenfelder has said outright that because the idea was long stigmatized as unscientific, almost no work went into building a real theory of it. So at present, all that exists are toy models. And critics counter that abandoning the independence of measurement choices would undermine the logic of every experiment ever done. It is a defended position, but on the evidence it remains a promissory note, not a theory. Retrocausal models, pursued by Hugh Price and Ken Wharton, take a different route again, preserving locality by letting a future measurement choice influence the past state of the system. They are elegant and actively developed, and a theorem by Leifer and Pusey showed that a genuinely time-symmetric account without retrocausality runs into contradiction, which gives the program real motivation. But no complete, experimentally distinct retrocausal theory yet exists, and the main objection, that it requires a suspicious fine-tuning to hide the backward influence, has not been answered. Here is the honest situation, and it is worth saying clearly rather than dressing up. On the question the title asks, these interpretations do not disagree. Everett, relational quantum mechanics, QBism, superdeterminism, retrocausality, Every one of them reproduces the no communication theorem, the frozen reduced state, the decoherence rates, the monogamy bound. They agree completely that the connection is real and mute. What they disagree about is what the connection is underneath, and here the evidence that would separate them is thin, precisely because they are, so far, built to make the same predictions. This is not a failure of the science. It is the science being honest about the boundary between what it has settled and what it has not. So let me name that boundary as plainly as I can, because it is the one genuine open edge in this whole subject, and it is not the edge people expect. The open question is not whether entanglement can reach you. That is answered by theorem, no. The open question is whether the quantum state behind the correlation is a real physical thing or merely a form of information. Two rigorous results sharpen this to a point. In 2012, Matthew Pusey, Jonathan Barrett, and Terry Rudolph proved that if independently prepared systems have independent real states, then the quantum state cannot be mere information about a deeper reality. It must itself be physically real. A year earlier, Roger Colbeck and Renner reached a related conclusion from a different assumption, that experimenters can choose freely. On that basis, they argued, the wave function corresponds one-to-one with a system's elements of reality. Both point toward the state being real, but both rest on assumptions, preparation independence, free choice, that thoughtful physicists can test. And there are consistent views, like relational quantum mechanics and QBism, in which the state is not a physical thing at all, but a relationship or an expectation. The evidence right now does not decide it. That is the honest edge. We can prove what the connection cannot do, with the full force of mathematics, and we cannot yet say what it is.
And I want to be careful, standing at that edge, not to fill it with something it cannot hold. When a question is really about the ultimate nature of what exists, why there is a quantum state at all, what its reality consists of at the deepest level, that question runs past what any current measurement can settle. The mathematics describes, with breathtaking precision, how the connection behaves. It does not tell us what it ultimately is, or why there is anything to be connected in the first place. That door the science leaves open, honestly, and it is not the place of the evidence to close it in either direction. What the measurement can settle, it has settled with theorems. What it cannot settle, it should not pretend to. Both halves of that are part of being serious. There is a number I have held back until now, and it belongs here, because it is the sharpest measure we have of exactly how strong the connection is allowed to be. When John Bell drew his line, he gave us a way to score the correlation between two distant measurements, a single quantity built from four combinations of settings, written as S equals E of A minus B plus E of A minus B prime plus E of A prime minus B minus E of A prime minus B prime. Let me translate that before the letters harden into noise. Each E is a measure of how strongly two distant results agree when the two experimenters pick particular settings. You add up three of those agreements and subtract the fourth, and the total is a single score for how correlated the two sides are. If the world ran on local pre-written answers, the sealed envelope picture, that score can never exceed 2. That is the classical ceiling. Quantum mechanics smashes through it. But here is the part that stopped me cold when I first understood it. Quantum mechanics does not smash through without limit. It stops at a precise, sharp, higher ceiling of its own. That ceiling was found by a mathematician named Boris Tsirelson in 1980, and it is called Tsirelson's bound. The quantum score can rise as high as 2 times the square root of 2, about 2.828, and not one hair higher. Think about how strange that is. Picture a high jumper who can clear a bar no human should be able to clear, sailing over a height that looks impossible. And yet, no matter how many times they try, they never once clear a bar even a centimeter above that. There is a second ceiling, invisible, absolute, sitting just above the impossible one. Why 2 times the square root of 2?
Why that exact value and no other? The correlation is stronger than any classical world permits, and yet it is disciplined, bounded, reined in by a limit as precise as anything in physics.
And here is where the story turns genuinely eerie, in a way that is rarely told. In 1994, two physicists, Sandu Popescu and Daniel Rawlik, asked a question that sounds almost childish but cuts to the bone. They asked what the world would look like if the correlation were even stronger, if it went all the way up to a score of 4, the absolute maximum that still forbids sending a signal. They invented a hypothetical device, now called a PR box, that would produce correlations that strong while still, remarkably, never letting you transmit a message. And the astonishing discovery was that such a super strong connection is not forbidden by the no signaling rule. You could, in principle, have a universe where distant things are far more tightly correlated than ours, and still no message could pass. So why does our universe stop at 2.828 instead of climbing to 4? What does it mean that nature chose? No, that is exactly the word I must not use, because nothing chose. What does it mean that our universe sits at this one precise value, stronger than classical physics allows, but weaker than the no signaling limit permits? That gap between 2.828 and 4 is one of the quiet, open puzzles of the field. The connection is real, it is bounded, and the reason it is bounded at exactly this value rather than another is not fully understood. Hold both ceilings in your mind for a moment, because together they draw the whole shape of the thing. Below, at 2, the world of sealed envelopes and pre-written answers, dead, ruled out by experiment. Above, at 4, a phantom world of connections stronger than ours, permitted by the no signaling rule but not realized in nature. And our universe, sitting precisely between them at 2 times the root of 2. The connection is real enough to break the classical ceiling by a wide, measured margin, and disciplined enough never to approach the phantom one. It is, if you sit with it, a connection carefully fenced on both sides, strong, but never strong enough to leak a word. Now I want to bring this out of the abstract and into a laboratory, because in 2021 something happened that makes the whole question of macroscopic connection stop being a thought experiment and start being an object you could, in principle, hold. 2 teams, one at the National Institute of Standards and Technology in Boulder, one at Aalto University in Finland, took not particles, not single atoms, but 2 tiny aluminum membranes, each shaped like a drumhead, and entangled them. Let me give you the scale, because it is the whole point. Each drumhead was about 20 micrometers across, roughly a fifth of the width of a human hair, 100 nanometers thick, weighing about 70 trillionths of a gram, and built from something like 1 trillion atoms. 1 trillion atoms. These are not quantum specks. These are objects you could, just barely, see under an ordinary microscope. And the teams put the 2 of them into a genuinely entangled state, and then did something even harder. They measured the entanglement directly, watched it, confirmed it. The physicist John Teufel, who led the NIST work, described what they saw in a way I find quietly perfect. If you look at each drum on its own, he said, it just looks hot, jittering with random thermal motion. Nothing special. Exactly the noise you would expect from a warm object. It is only when you look at the 2 of them together that you see the truth. What looks like the random shaking of one drum is precisely correlated with the shaking of the other, in a way that is only possible through quantum entanglement. Stop and notice how exactly that echoes the 2 accountants. Each ledger alone, meaningless noise. Each drum alone, just hot. The connection lives only in the comparison. Here it is, not in a metaphor, but in aluminium you could touch, at the scale of a dust mote. A real, verified, macroscopic entanglement, and still, looked at from either side alone, invisible. Still mute. Still nothing you could feel by holding one drum and asking it about the other. But wait,
Does this not contradict everything I said about decoherence? If a trillion-atom object can be entangled, why did I insist that macroscopic connection evaporates instantly? This is the objection you should be forming, and it is the right one, and the answer sharpens the whole picture rather than softening it. The drumheads stay entangled only because the teams fought decoherence with everything they had, cooling the system to within a whisper of absolute zero, isolating it inside a superconducting circuit, shielding it from the storm of air and light and heat that would otherwise shred the connection in a fraction of a nanosecond. It is exactly like keeping a snowflake intact, possible, but only inside a freezer built for the purpose, and only for as long as the freezer holds. Take those drums out into a warm room, and the entanglement is gone before you could blink. Gone, in fact, 10 to the 30-something times faster than a blink. The experiment does not overturn the coherence wall. It proves how ferociously you must work to hold it back, even for an instant, even at a fifth of a hair's width. Nothing about a body, warm and open and awash in its environment, comes remotely close. There is an even more startling version of this from a decade earlier that I find almost hard to believe, though it is well documented. In 2011, a team led by researchers at Oxford managed to entangle two macroscopic diamonds, millimeter-sized, visible, sitting at room temperature 3 centimeters apart on a bench. Two diamonds you could see with your naked eye, sharing a genuine quantum connection. But read the fine print, because the fine print is the whole story. The entanglement lasted about 7 trillionths of a second, 7 picoseconds at room temperature, before decoherence swallowed it. That is the shape of every macroscopic connection ever made, real, verified, and fleeting to the point of non-existence by any human standard. You can build the connection at large scales. You cannot make it last, and you can never, ever feel it. What does it mean that we can entangle diamonds you can see and drumheads made of 1 trillion atoms, and yet the connection still cannot be felt, cannot be used, cannot be held? It means the barrier was never about size in the naive sense. It was never that big things cannot be quantum. It is that big things cannot stay quantum in contact with the world, and cannot leak a signal even while they are. The walls are not about scale, they are about isolation and information, and both hold at every size we have tested.
Let me follow one more thread because it reaches into the most intimate place of all, the possibility that quantum connection does something inside your own body that matters, that some of the machinery of thought or feeling runs on it. We saw Tegmark close the door on the brain as a place where quantum superposition survives long enough to compute, but there is a subtler proposal, and it deserves a fair and full hearing because it comes from a serious physicist and it is designed precisely to slip past Tegmark's argument. The physicist is Matthew Fisher at the University of California, Santa Barbara, and in 2015 he asked a careful question. Tegmark showed that the electrons and the large molecular structures in the brain decohere almost instantly. But what about nuclear spins, the tiny magnetic orientation of an atom's core, which is far more isolated from the surrounding electrical storm than any electron? Fisher zeroed in on one atom in particular, phosphorus. The phosphorus-31 nucleus has a spin of 1/2, which makes it a natural quantum bit, and it is buried deep enough inside its atom to be shielded from much of the noise that destroys everything else. His proposal is intricate and genuinely clever. When certain phosphate molecules are broken apart by an enzyme in the body, the two phosphorus nuclei that separate could, he argued, be left in an entangled singlet state, quantum connected. Those phosphates could then be taken up into a specific structure, a calcium phosphate cluster called a Posner molecule, about a nanometer across, which Fisher proposed might act as a natural shield, protecting the fragile nuclear spin entanglement from decoherence for an extraordinarily long time. How long? Fisher and his colleagues conjectured,
and I want to stress that word, conjectured, that Posner pairs might stay entangled for a day, or possibly much longer. A day, inside a warm, wet, living body. If that were true, it would be the one exception to everything I have laid out, a place where quantum connection survives long enough to do biological work. So is it true? Here is where I have to be scrupulous, because this is exactly the kind of tantalizing idea that is easy to overstate. It is unproven, it is a hypothesis, a carefully constructed possibility, and some recent experiments have argued against the specific mechanism it needs. Fisher himself has been admirably honest about the stakes, and his own framing is worth quoting because it shows what real science sounds like at its edge. He said that if phosphorus nuclear spin is not being used for quantum processing, then quantum mechanics is not operative on long timescales in cognition, and that ruling this out is important scientifically. It would be good, he said, for science to know. Read that carefully. He is not claiming victory. He is proposing a sharp, testable possibility and inviting the world to prove him wrong. And even if his conjecture were fully vindicated, even if Posner molecules do shelter entangled phosphorus spins for a day inside your bones and brain, notice what it would and would not mean. It would be a stunning discovery about quantum effects in biology. It would still not be a connection you could feel, or send a message through, or extend to a distant person. The no communication theorem would still hold over every one of those spins. The reduced state would still be frozen. Even the boldest frontier of quantum biology, if it pays off, does not breach the walls. It operates entirely inside them. This is the part that stays with me. Every place we look for an exception, the bird's eye, the aluminium drum, the diamond on the bench, the phosphorus in the bone, we find the same shape. Quantum connection is real, and it is either fantastically brief, or fantastically small, or provably mute, or all three at once. The walls do not have a door in them. They have only different faces, and every honest search for a way through has come back with the same answer. There is one frontier where physicists are genuinely unsure whether entanglement even applies, and it is the one that governs the largest structures in existence, gravity. Everything we have discussed lives in the quantum world of particles and fields, but gravity so far has resisted every attempt to fold it fully into that world. And so a beautifully simple question sits open. Can gravity itself generate entanglement? If you took two small masses and let nothing but their mutual gravity act between them, would they become quantum connected? In 2017, two independent teams, one led by Sugato Bose, another by Chiara Marletto and Vlatko Vedral, proposed an experiment to find out, because the answer would settle something enormous. If gravity can entangle two masses, then gravity itself must be quantum. If it cannot, then gravity may be something fundamentally different from everything else in physics. The trouble is a number, and the number is almost comically discouraging. Gravity is weak. Not a little weak, the strength of the gravitational attraction between two small particles is about 43 orders of magnitude smaller than the electric force between them. 43 zeros. To feel how absurd that gap is, picture trying to hear a single whispered word in one city while every stadium, every jet engine, every thunderstorm on Earth roars at once. That is the signal-to-noise problem of trying to watch gravity entangle two masses. The entangling effect it would produce is a phase. You can write it, roughly, as g times mass squared times time, divided by h bar times the separation. And every term in that expression conspires to make it minuscule. It is why the experiment has been proposed but not yet performed. It sits at the very edge of what might someday be measurable, and whether it can be done at all is an open question. But notice even here, if gravity does entangle two masses, that connection too will obey no communication. It will be real and it will be mute. The walls extend even into the parts of physics we have not yet mapped. Let me gather the mathematics of exclusion one more time, because monogamy is subtle enough to reward a second look, and there is a piece of it I have not yet shown you. When physicists measure how entanglement is shared among three parties, they use quantities with almost tactile names, the concurrence and the tangle for pairs, and something called the three-tangle for what is left over. The three-tangle is written as the total entanglement one system shares with the other two together, minus what it shares with each of them separately. Turn that into a picture. Imagine a shared inheritance divided among relatives. Some of it goes to purely one-on-one bonds, this person with that person. But there can be a residue, a portion of the connection that belongs to all three at once and cannot be assigned to any single pair. That irreducible, genuinely three-way share is the three-tangle. It tells you that entanglement is not only limited in how much can be shared, but comes in distinct flavors, bonds between pairs, and a deeper communal bond that binds the whole group in a way no pair of them owns alone.
Why does that matter for the question of whether you are alone? Because it shows, in hard mathematics, that connection has a fixed and finite structure. It is not a free-flowing substance that pools wherever it likes. It is budgeted, partitioned, exclusive, and the deeper the pairwise bond, the less of that communal three-way tangle can exist, and the more each system is walled off from the rest. The universe does not permit a connection that is both maximal and universal. The mathematics of the three-tangle is one more brick in the wall against the dream of everything deeply bound to everything. I know this has been a long climb through a great deal of machinery, density matrices and localization rates, tangles and Tsirelson's bound, drumheads and Posner molecules. So take one ordinary thing and let it carry all of it. Look at a shadow on the floor, the sharp, dark shape of an object thrown by the light. That crisp edge exists because photons stream off the object in their trillions, each one carrying away a copy of exactly where the object is. The very redundancy Zurek called quantum Darwinism, the environment broadcasting a classical fact so many times that anyone can read it. The solidity of that shadow, its dependable sameness whether you look or not, is quantum connection being dispersed and overwritten, ceaselessly at the speed of light. You are surrounded, right now, by the visible aftermath of connection being erased. It is the most ordinary thing in the room, and it is the reason the room feels solid and separate, rather than ghostly and joined. For completeness, there is one more account of quantum reality worth naming, because it takes the opposite stance to Everett and yet reaches the same verdict on the connection. Some physicists, following the work of Louis de Broglie and later David Bohm, hold that particles do have definite positions at all times, guided by a real wave that fills space. In that picture, there is no branching universe and no relativity of states. There is one world, with particles on definite paths. But this account buys its clarity with an explicit, built-in non-locality. The guiding wave links distant particles directly, so that the setting of a distant measurement instantly shapes the motion here. And yet, here is the point that matters for us. Even this most vividly connected of all the pictures cannot be used to signal. The statistical fog that hides the particles' exact positions is precisely thick enough to keep the reduced state frozen and the no communication theorem intact. So we have surveyed the whole landscape of serious accounts: the branching universe, the guided particle, the relational state, the agent's expectation, the superdetermined world, the retrocausal one. And every single one of them, whatever else it disagrees about, agrees on this. The connection is real, and it carries nothing. That unanimity, across accounts that agree on almost nothing else, is the strongest signal we have that the answer is not an artifact of one interpretation. It is structural. It is baked into quantum mechanics itself. What does it mean that theories which cannot agree on what reality fundamentally is, nonetheless agree, perfectly, that the connection cannot be felt? It means we have found something rare in physics, a conclusion so robust that it survives every disagreement about the deeper story. You do not often get that. Usually the interpretation changes the answer. Here it does not.
And that is exactly why I can speak about the muteness of the connection with confidence, while remaining genuinely, honestly uncertain about its ultimate nature.
Now let me return to the threads I asked you to hold, because it is time to weigh them against each other and see clearly what the whole body of evidence supports. Early on, I said the word connection was half right and half wrong, and that the same mathematics that makes the connection real is what proves it can never reach you. Every wall we have walked has confirmed that. The correlation is real, Bell violations to 11.5 standard deviations, dead certain. And the connection is mute, the no communication theorem, standing on the frozen reduced density matrix, a theorem and not an opinion. I asked you to keep the localization rate in mind, 10 to the 36th, air molecules on a dust grain, and it returned as the coherence wall, the reason no macroscopic connection survives to be noticed. I asked you to hold the idea that the deepest picture of connection, Everett's universal wave function, would come bundled with the reason you cannot feel it, and it did, through decoherence and Ein selection, and the redundant classical world that Zurek's quantum Darwinism experiments confirmed in Diamond. And monogamy, with its tangles and its three-tangle, took the sweetest version of the belief, everything bound to everything, and showed it to be not merely unproven, but mathematically forbidden. So which explanation does the evidence support? On the question the title asks, can the connection reach you? Can it be felt? Can it be used? Can it be spread to all things? The evidence is not close. It supports decisively a single answer, no. And it supports that answer not through one theory, but through theorems that hold across every theory, and through decoherence rates that have been measured, and through macroscopic entanglement experiments that show the connection is real, precisely where it is also fleeting and mute. Where each rival account strains, Everett on deriving probability, relational quantum mechanics and QBism on stepping back from an observer-independent world, superdeterminism on having only toy models, retrocausality on fine-tuning, none of those strains touch the verdict on the connection. They strain over what the connection is. They agree entirely on what it does. And that leaves the one honest open edge, standing exactly where the mathematics runs out. We can prove, with the full force of theorem and experiment, that the connection carries no signal, cannot be felt, cannot survive in a body, cannot be shared with everything. What we cannot yet say, what no current measurement decides, is what the connection actually is. Is the quantum state behind it a real physical thing, as Pusey, Barrett and Rudolph argued under their assumption of preparation independence, and as Colbeck and Renner argued under their assumption of free choice? Or is it, as Rovelli's relational quantum mechanics and the QBists hold, not a thing at all but a web of relationships, or a set of an agent's calibrated expectations? The evidence does not decide. The theorems that would decide it rest on premises that thoughtful physicists still contest. That single question, the ontology of the state behind the correlation, is the genuine open edge of this entire subject, and it is honest to say plainly that it is open, and honest not to close it in either direction. Here is the puzzle I planted a while ago and left hanging, the one last uncomfortable question, and I can resolve it now. It was never whether the connection can reach you. That is settled by theorem, and the answer is no. The real question underneath the whole title is stranger and quieter. In what sense are you connected to the distant world at all, if the connection can do nothing you could ever detect? And the answer the mathematics gives is the one I keep circling back to, because it inverts everything the intuition expects. You are connected, genuinely, in the deepest reading of the universal wave function. You and the distant world may be one single entangled state, but you are so completely entangled with everything immediately around you, drowning in connection at a rate of 10 to the 36th per second, that any thread reaching out to anything far away is diluted past all detection. The reason you feel alone is not that you are disconnected. It is that you are connected to everything at once, so totally and so indiscriminately that no single connection can ever stand out to be felt.
A connection so complete it is indistinguishable from the inside from being utterly separate. That is the resolution the science supports, and it is worth stating without hedging. The connection is real, and it was never yours to feel, not because it is too faint, but because the very completeness of your entanglement with the world is what makes any single strand of it invisible. The mathematics that binds you to everything is the same mathematics that seals each of us inside our own local view, both at once. And the one thing the equations do not tell us, the thing they leave standing open in the dark past the last theorem, is what that binding at its root truly is. A real thread woven into the world, or only the shadow that relationships cast when systems meet? That question the measurements cannot yet settle, and it would be dishonest to pretend otherwise. When two particles are entangled in a pure joint state, a state we know completely, with no uncertainty at all, and you take the partial trace to find the local state of just one of them, something remarkable happens. The local state comes out mixed. Not pure, that word matters. A pure state is one you know everything about. A mixed state looks, locally, like ordinary classical uncertainty, as if the particle simply had some definite value you happen not to know. So here is the strange truth at the heart of it. You can have complete, perfect knowledge of the pair, and yet each half, examined alone, looks as ignorant and ordinary as a coin you have not yet looked at. The information has not vanished, it has moved. It lives entirely in the correlations between the two, and not at all in either one. Picture a coded message split across two sheets of transparent film. Each sheet alone, held up to the light, shows nothing but random speckle, genuinely random, with no pattern a codebreaker could ever extract. Only when you lay the two sheets precisely on top of each other does the message spring into view. The information was never on either sheet. It was in the alignment, the relationship, the overlay. That is what a pure entangled state is. And it is why the local view, the single sheet, the reduced density matrix, is not just hard to read, but provably empty of the connection. There is nothing on your sheet to feel, because the message was never written on your sheet at all. It was written in the space between, a space you cannot reach without physically bringing the other sheet to yours.
This is the point at which the eeriness of entanglement finally resolves into something almost calm. The connection is not a signal that is being blocked, it is not a message that is too faint, it is information that, by its nature, exists only in a joint pattern that no single party holds any piece of. What does it mean that two systems can share a perfect, complete description while each, alone, knows nothing? It means that the deepest form of togetherness the universe permits is also, from the inside of either partner, indistinguishable from complete solitude. The togetherness is genuine, it has no local face. Let me trace how confidence in this picture was built up experimentally, because the story is a slow tightening of the noose around every possible loophole, and it did not happen overnight. The correlations that break Bell's ceiling could, for decades, be doubted on technical grounds. Maybe the detectors were too inefficient and only caught a biased sample of particles. Maybe the two ends of the experiment were close enough that some slow influence, traveling below light speed, could have coordinated them. These were called the detection loophole and the locality loophole, and closing both at once, in a single experiment, was the great challenge. In 2015, a team in Delft, led by Ronald Hansen, did it, using electron spins trapped in nitrogen vacancy centers, tiny atomic defects inside diamond, separated by 1.3 kilometers across the university campus. They entangled those distant spins and measured the correlation with the detectors far enough apart that no light-speed signal could have coordinated them, and efficient enough that no biased sampling could explain the result. The score came out at 2.42, comfortably past the classical ceiling of 2, with a probability of only about 4% that it was a fluke. It was the first time the connection had been confirmed with every major loophole shut in one stroke. And even that was not the end of the tightening. There remained one last, almost philosophical escape route, the freedom of choice loophole.
What if the settings the experimenters chose were somehow subtly correlated, in advance, with the properties of the particles? To close that, physicists reached, quite literally, for the sky. They used the light of distant stars, and later the light of quasars billions of years old, to set the measurement choices. Light that left its source long before the experiment, in some cases before the Earth existed, so that no ordinary process could have coordinated it with the particles in the lab. Ancient light, older than the solar system, choosing the angle of a polarizer in a laboratory tonight. The correlations held. The connection is real under every test we have been able to devise, and each closed loophole has only sharpened the same verdict. What does it mean that we had to borrow light from the edge of the observable universe just to rule out a coordinated conspiracy, and the connection survived even that? It means the correlation is about as securely established as any fact in experimental physics, and that whatever it is not an artifact of our instruments or our choices.
The march toward larger and larger quantum objects is worth laying out as its own arc, because it shows precisely where the border between the quantum and the classical sits, and how hard-won every inch of it is. For most of the 20th century, quantum behavior was something you saw in single particles, or at most in small molecules. Then the experiments began to climb. In 2013, a team demonstrated interference, the signature of a single object being in two places at once, with molecules of around 10,000 atomic mass units, built from more than 800 atoms. 6 years later, in 2019, the same lineage of experiments in Vienna and Basel pushed it to more than 25,000 atomic mass units, 2,000 atoms, in that 2-meter interferometer I mentioned. Each step up that ladder is exponentially harder, because the larger the molecule, the more fiercely the environment decoheres it, and the more perfectly you must isolate it. The trend line is unmistakable, and it points to a boundary that is not a hard wall of principle, but a practical cliff of decoherence. Quantum behavior is available at any scale, in principle, but the price of admission, the isolation you must buy, rises so steeply that a grain of dust, let alone a fingertip, is forever out of reach. That practical cliff is exactly what makes the pointer states so important, and I want to return to Zurek's Ein selection with a sharper example, because it answers a question you may not have known to ask. Of all the properties a large object could have, position, momentum, energy, and countless stranger quantum combinations of them, why is it always position that comes out sharp and definite in the everyday world? Why do we never see a chair smeared across two locations, even though quantum mechanics permits such states to be written down? Zurek's answer is that the environment does the selecting, and it selects the property it most readily monitors. Air molecules and photons scatter off an object depending on where it is. They carry away position information constantly. So position is the property the environment measures relentlessly, and therefore position is the property that gets pinned down, made classical, robust. A superposition of two positions is destroyed almost instantly, because the environment is, in effect, screaming the object's location in every direction at every moment. Momentum superpositions, energy superpositions, these decohere too, but position is the environment's favorite target, and that is why the world you see is a world of things in definite places. Consider what this means with an everyday object. Set a coffee cup on the table. Quantum mechanics, taken literally, allows a state in which that cup is spread across two spots at once. You never see it, and now you know exactly why. The moment such a state formed, the trillions of air molecules and photons bombarding the cup would each carry off a record of which spot, and that flood of records, the same redundancy Zurek called quantum Darwinism, would collapse the two-spot state into one definite location faster than any conceivable clock could tick. The cup is classical not because quantum mechanics fails for large things, but because quantum mechanics, applied honestly to a thing drowning in its environment,
produces exactly the solid, single-location cup you see. The classical world is not a different world with different laws. It is the quantum world, seen through the fog of overwhelming decoherence. There is a competing account of why measurements yield definite outcomes that I have not yet given its due, and fairness requires it, because it takes the opposite stance to Everett on the most basic question of all. Some physicists, following a model developed by Girardi, Rimini and Weber, the same Girardi who helped prove the no-communication theorem, propose that the smooth quantum evolution is not the whole story, that there is a genuine physical collapse, occurring spontaneously and at random, extremely rarely for a single particle, but overwhelmingly often for a large object made of enormous numbers of particles. On this view, there is no branching universe and no mere appearance of collapse. Collapse is real, a new physical process added to the theory. Its great virtue is that it takes the definiteness of the world at face value, and even makes slightly different predictions from standard quantum mechanics, which means, unlike the pure interpretations, it could in principle be tested and ruled out. And here is what matters for our question. Even in this objective collapse picture, entanglement still cannot signal. The spontaneous collapses are random and uncontrollable, so they cannot be used to send a message. The reduced state stays frozen against anything a distant partner deliberately does. Once again, a completely different account of reality and the same verdict on the connection. I keep being struck by that convergence, and I think it is the single most important thing to carry away from the whole subject. The branching universe of Everett, the guided particles of Bohm, the relational world of Rovelli, the personal expectations of the QBists, the superdetermined cosmos of 't Hooft and Hossenfelder, the retrocausal models of Price and Wharton, the spontaneous collapses of Girardi and his colleagues. These accounts disagree with each other about almost everything that can be disagreed about. They paint wildly different pictures of what is fundamentally real. And yet on the question of whether the connection between two entangled things can carry a signal, or be felt, or be used, they speak with one voice: no. When theories that agree on nothing else all agree on one thing, that one thing is not a feature of any single theory. It is a feature of the world. Let me anchor the human weight of this with one more everyday moment, because it is easy to lose the person in the mathematics. Think of standing at a window at night, looking up at a star. The light entering your eye left that star years, perhaps millennia ago. There is a real physical thread there, photons that traveled the whole way and are now bending molecules in your retina, a genuine causal connection you can feel, as warmth, as light, as sight. That is what an ordinary connection is. Something crosses the space and something changes on your side. Now hold that against quantum entanglement. If you were entangled with that star, there would be no photon, no crossing, no change in your retina, nothing for a nerve to fire on. The entanglement would be real, and it would be silent, the exact opposite of the starlight, which is faint and slow and utterly perceptible. The starlight connects you across unimaginable distance and time, and you feel it. The entanglement connects you and you feel nothing. That contrast is the whole subject in a single glance out a window. The connections we can feel are the ones where something travels, and entanglement is the connection where nothing does.
What does it mean that the universe offers two entirely different kinds of connection, one that reaches you and one that never can? It means the word connection, which we use for both, was hiding a distinction the physics makes sharp. A causal connection, where influence propagates and can be felt, and a correlational connection, where a shared pattern exists but nothing propagates and nothing can be felt. Entanglement is purely the second kind. It is real, it is deep, it is confirmed past doubt, and it belongs to a category of connection that by its nature has no local face. The loneliness of the quiet room and the entanglement of the universe are not in contradiction. They are answers to two different questions, and we had been asking them as if they were one.
I return often to a way of putting it that Zurek's work makes precise. A macroscopic body is not a lonely island that occasionally reaches out to touch distant things. It is the most thoroughly connected object imaginable, bound at every instant to the uncountable particles of its surroundings, its every property continuously recorded and rebroadcast by the environment. And it is exactly that total, saturating connection to what is near that erases any special connection to what is far. You cannot feel a thread to a distant star because you are woven completely into the fabric immediately around you, and that weaving dilutes every distant strand into invisibility. The isolation we feel is the shadow cast by a connection so complete it leaves no single strand to grasp. That is the resolution the evidence supports, laid out in full and weighed against every serious rival. The correlation is real, confirmed to 11.5 standard deviations, loopholes closed, ancient starlight enlisted to seal the last escape. The connection is mute, the no communication theorem and the frozen reduced density matrix, theorems that hold across every interpretation. The connection cannot survive in a body, decoherence at 10 to the 36th per second on a dust grain, the brain losing coherence 10 trillion times faster than a thought forms. And the connection cannot be universal, monogamy and the three-tangle forbidding the deep bond to everything. 4 walls, each built of the same mathematics that makes the connection real, and every one of them holds. The science has answered the question the title asks, and it has answered it completely. The connection is real, and it can never reach you.
And yet, standing at the edge, there is a question the mathematics does not answer, and it would be a failure of honesty to paper over it. We can say with the certainty of theorem what the connection cannot do. We cannot yet say what it is. Whether the quantum state behind the correlation is a real physical thing, as the theorem of Pusey, Barrett and Rudolph suggests under the assumption that independently prepared systems have independent states, and as Colbeck and Renner's result suggests under the assumption that experimenters choose freely, or whether it is not a thing at all, but a relationship, as Rovelli's relational quantum mechanics holds, or a set of an observer's own calibrated expectations, as the QBists hold. The experiments that would decide between a state that is physically real and a state that is merely relational have not been performed, and may not be possible with anything we currently know how to build. The premises that would settle it are premises reasonable physicists still dispute. That single question, the ontology of the state behind the correlation, is the honest open edge, and it sits precisely where the equations stop describing behavior and would have to start describing being. There the science reaches its limit, and it is honest to say so, and to leave the question standing open rather than answering it with more than the evidence contains. So consider, one last time, the quiet room where we began, and the intuition that if you were truly connected to something far away, you would feel it reaching across the empty space. That intuition was not foolish. It was half right in the most profound way. You are connected, threaded into a single quantum state with the whole of the world, entangled beyond any hope of separation. It was only wrong about the reaching. The connection has no reach, no thread you could feel tugging, no channel a message could ride, no way to gather the whole universe into a bond you could hold, because the very completeness of your entanglement with everything near you is what dissolves every strand to everything far. Quantum entanglement gives us the strongest statement of togetherness that physics has ever written down, and in the same breath, in the same equations, it proves that togetherness this total is, from the inside, indistinguishable from being alone. The reduced density matrix stays frozen. The localization rate erases every macroscopic trace. Monogamy forbids the universal web. Everett's one wave holds you and the distant star in a single state you will never experience as one. All of it true at once, and none of it a contradiction. Only the discovery that connection, at the deepest level, was never the kind of thing that could be felt.
There is a measurement from the black hole story I want to bring back into the light because it shows the monogamy principle doing its most dramatic work on the largest possible stage, and it deepens everything we have said about how connection is budgeted. Don Page's insight in 1993 was that when a black hole slowly evaporates, the radiation streaming away becomes more and more entangled with what has already escaped, and the entanglement entropy, the measure of that connection, climbs steadily upward. But it cannot climb forever, and the reason it cannot is monogamy. A newly emitted particle would, in the naive picture, be entangled both with its partner falling into the hole and with the vast cloud of radiation already emitted. Monogamy forbids it from being strongly entangled with both at once. Something has to give. And what gives, at the moment now called the Page time, is that the entanglement stops rising and begins to fall, tracing out the curve that carries Page's name. That turnover is the signature that information is not lost but preserved, threaded out of the hole in the correlations of its own radiation. The same exclusivity that stops two lab particles from sharing a bond with a third is what, on the scale of a collapsing star, may rescue the universe's bookkeeping of information itself. What does it mean that the humblest theorem about sharing, you cannot be maximally bound to two partners at once, governs both a pair of photons in a laboratory and what becomes of everything that ever fell into a black hole? It means the rules of connection are not scale-dependent add-ons. They are woven into the structure of reality at every level we have been able to look. Think about that reach for a moment, because it is easy to let the numbers slide past. The monogamy relation was proven for three simple quantum bits, the most abstract, stripped-down objects imaginable. And the very same principle constrains the entanglement entropy of Hawking radiation from an evaporating black hole, an object with the mass of stars, across timescales longer than the current age of the universe by unfathomable factors. One inequality, tau of A minus B plus tau of A minus C at most tau of A with B and C together, and it holds from the smallest system we can build to the largest catastrophe the cosmos can stage. The connection is finite, budgeted, and exclusive, whether it lives between two trapped ions or between the inside and outside of a hole in spacetime. I find that unity across 40-odd orders of magnitude of scale to be one of the quietly astonishing facts in all of physics. A single rule of sharing that neither the smallest nor the largest thing in the universe is permitted to break. And this returns us from the edge of a black hole all the way back to the aluminium drumheads on the laboratory bench in Boulder, to the same lesson wearing different clothes. When John Teufel's team looked at their two entangled membranes and saw that each one alone looked merely hot, while the pair together revealed a correlation only entanglement could produce, they were watching monogamy and no communication and the frozen reduced state all at work in a single object you could nearly see. The drum on the left, examined alone, is a warm, jittering thing with no message in it, its reduced density matrix as blank as the Tokyo accountant's ledger. The connection is entirely in the joint pattern, retrievable only by bringing both records together, exactly as the two transparent films only spell out their message when overlaid. Macroscopic, verified, real, and still, from either side alone, silent. The theorem that governs the black hole, and the theorem that governs the drumhead, and the theorem that governs the quiet room are one theorem, and it says the same thing in every voice. The connection is in the between, never in the one, and the one can never reach across to feel it. So the full weight of the evidence settles into a single shape, and it is worth holding it whole. Quantum entanglement is a genuine, experimentally ironclad correlation, Bell's ceiling broken to 11.5 standard deviations, Tsirelson's bound of 2 times the square root of 2 marking its exact and disciplined strength, ancient quasar light enlisted to close the last loophole. It is real at scales from single electron spins in Delft Diamond to trillion atom drumheads in Boulder. And across every one of those scales, and across every serious account of what quantum mechanics means, It carries no signal, changes no local quantity, survives no macroscopic contact with the world, and refuses to bind itself universally to everything. The connection is real, the connection is mute, both proven together. If you have walked this whole way with me, then the question the title raised has its answer, and it is not the comfortable one and not the bleak one, but something stranger and truer than either. Quantum entanglement, quantum non-locality, the universal wave function, the no communication theorem, the monogamy of entanglement, the decoherence that dissolves every macroscopic trace, each of these was a step in the same argument, and the argument closes cleanly on the science while leaving one door, and only one, honestly open. The evidence shows that you are entangled with the world, in the deepest reading, that you and the farthest star share a single quantum description, one wave, never truly factored into separate pieces. The evidence shows, with equal force, that this connection is frozen out of your local view, dispersed across uncountable particles 10 to the 36th times a second, forbidden by monogamy from binding you deeply to all things at once, and sealed by theorem against ever carrying a message or a sensation. And the evidence stops, honestly, at the one question it cannot yet reach. What that connection is, underneath, a real thread woven into the fabric of what exists, or the shadow that relationships cast when systems meet. That question the mathematics does not close, and it would be false to close it for them. Consider what the migratory robin actually tells us when it turns its head to find north, because that small living compass carries the whole lesson in miniature. The cryptochrome in its eye holds a pair of electron spins in a fragile quantum relationship for about a millionth of a second, and in that flicker the bird reads the geometry of the Earth's magnetic field. It is the clearest case we have of quantum coherence doing real biological work, and it works only because it is fast, small, and shielded, gone before the environment can dismantle it. The bird does not feel a magnetic thread stretched across a continent. It runs a chemical calculation inside a single molecule, over and over, each one lasting a microsecond. Even life's most successful use of the quantum world obeys the same law as everything else. Coherence lives only where it is fleeting and tiny, and the moment you scale it up to a whole animal, a whole nervous system, a whole felt experience, decoherence has already erased it. The robin's compass is not an exception to the walls. It is a demonstration of exactly how narrow the gap in them really is. And that narrowness is the through line of the entire subject. From Schulten's radical pairs in a bird's eye to Fisher's conjectured phosphorus spins in the bone, from Fein's 2,000 atom molecules held in a 2-meter interferometer to Teufel's trillion atom drumheads cooled to a whisper above absolute zero, from Henson's Delft diamonds across 1.3 kilometers to Page's radiation leaking from a black hole, every case tells the identical story. The connection is real wherever we look for it, and everywhere it is either fantastically brief, fantastically small, or provably mute. There is no crack. There is no scale, no substance, no living tissue where entanglement becomes a thread you could feel tugging from far away. The universe permits the connection and forbids the sensation, in the same equations, with the same certainty. What the evidence settles, it settles completely. Quantum entanglement is genuine, quantum non-locality is confirmed, and the no communication theorem, the monogamy of entanglement, and quantum decoherence together prove that this connection carries no signal, can never be felt, cannot survive in anything as large as a body, and cannot bind you to all things at once. That much is theorem, measured to 11.5 standard deviations and sealed with the light of ancient quasars. And where the science reaches the one question it cannot answer, what the connection is, at its root, a physical thing or only a relation among systems, the ontic state of Pusey, Barrett and Rudolph, or the relational one of Rovelli and the QBists. It stops and names that edge plainly, and leaves it open, because that is what honesty at the limit of measurement requires. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds.
So return one final time to the quiet room and to the intuition that started us, that a real connection would be something you could feel reaching across the empty space. You were not wrong to feel connected. You are woven into a single quantum state with the whole of the world, entangled past all separation, threaded into everything near you so completely that the loneliness you feel is not the absence of connection, but its overwhelming presence, diluted past all sensation. The reduced density matrix stays frozen. The dust in the sunlight is torn from the quantum world 10 to the 36th times a second. Monogamy forbids the universal web, and one unbroken wave holds you and the farthest star in a togetherness you will never once experience as togetherness. The connection is real. It was simply never yours to feel. And in the space where the equations fall silent about what it truly is, the oldest question of all still waits, patient, undimmed, and open.